So, hello YouTube. We're now recording. I'll try not to swear. We're basically going to pick up from the cliffhanger. I've got a page for this lecture. What's going on? Actually, when I first typed that, I mistyped it. What's going on? Because I was sort of channeling the Buddhist in my soul. Okay, so this is a very short lecture page because it's just a jumping off point to the things we actually need to do. So I think I actually have, inevitably, Zoom is, the way cats always, they know where you're going to be in 10 seconds time and they move there to be in the way. But Zoom is like that with this. They just about managed to get there. So goodbye, Fred. We'll see Fred in semester 2. Welcome back, Clemens. Didn't get knocked over by a drone. And thank goodness. We were in the business of proving that multiplication is associative. And I've written a whole load more content on that than was there on Friday, just talking through the ideas very slowly. So please do refer to that and see what's really going on. So what happened, let me see, we did this, we figured out, we did the why is it stuck thing, and we figured out that both sides of the equation are stuck because we need more information about C. So we said inductively C from C test. And the base case, when C is 0, that just computes down to 0 equals 0. So ask doesn't even trouble you with it. The step case, it's the case where C is the successor of something and the something is called X. So the point is that X is smaller than C. So we are entitled to assume that what we're already trying to prove about C, what we're trying to prove about C is already true for X. The reason why this explanation makes sense is that we reduce a complicated problem into a simpler problem, and it can't keep getting smaller forever. You eventually get to the limit. Okay, so that in particular means we know this equation. So this is, where did I get this equation from? I replaced C by X in the original goal. Everybody with me so far? I'm going to do the Alistair thing. Yes? So what I'm saying is we're working inductively, which means whatever variable we pick to be inductively on, we have to prove the statement for that variable, but we are allowed to assume the statement for everything smaller than that variable. And we know X is smaller than C because C is the successor of X. And correspondingly, we are entitled to the knowledge that multiplication is already associative when the third number that we're multiplying is X. Okay, so that's good information, and it's good for you to write a comment that says what you know inductively, because the way you do these proofs is to swim towards the opportunity to use what you know inductively. Okay, so what happened here after we did test, we got a bit of computation, and you can see one copy of A times B bubbled out to the front. And here we've got A times B times X, the rest of the calculation. And the right-hand side has turned into A times this thing, where a B plus has bubbled out to the front. Now, here's the way you play this game, right? This game is not random or magical. This game is very, very deliberate once you know what you're looking for. You can see here, there's an A times at the front on the right-hand side. And at the front on the left-hand side, there's a plus. And inside the plus, you got an A times here. So that's almost useful because we're trying to get the two sides to match. So we need to make them more and more similar. You see here, there's an A times quite deeply buried. And we would like to get it closer to the right-hand side. We want to bubble that A times outwards. So fortunately, the induction hypothesis that we're entitled to is exactly telling us how to move the A times one layer further to the front. So that's useful to us. That's definitely progress to make the left-hand side, because you can see here on the left-hand side is the very thing the induction hypothesis is talking about. So it's definitely progress to replace this sub-expression that I have highlighted by the other side of the equation in the induction hypothesis. So the way we do a proof that takes several steps to get there of equational reasoning. So you might, I lined this up in advance, you might remember, like at school, proving equations by saying something like this, like left-hand side is this, equals that, equals the other, and eventually in little steps you get to the right-hand side. Is this familiar? Is a thing you have done? Okay, so people think by root is this great mystery, but it's not. It's just the ask way of doing a proof that looks like this on a piece of paper. All you do is you say, whatever your next step is, you say by root with that thing. So here we say by root with this thing here. So you can see what's happened. All I've done is rewritten one sub-expression by the induction hypothesis. I've just moved the brackets so that A times is slightly further up. Okay. So then when you say by root, you get two sub-goals. The thing here, so we're proving left-hand side equals right-hand side. And what we do with by root is we offer up something that lives in the middle. And we're then asked to prove left equals middle and middle equals right. And if we've chosen something sensible to be the middle, then both of those things should be easier than what we started with. So hopefully it's progress. And here, left to the middle looks like something plus something equals something plus something. And that's where we deploy this under business. Let me give you a silly example. If I say prove Connor plus Clemens equals panic plus terror, and then I say under plus, and I have to put the plus in brackets because plus is an infix operator, right? And I hit send, then after an interminable delay, something will happen. Yes, you see what comes back is that we make progress by proving Connor is panic and Clemens is terror. So what we're saying is the explanation for why these two uses of plus give us equal outputs is that we're giving them equal inputs. Now, you know, for plus, that isn't always a good idea, because although 2 plus 2 is 4 and 3 plus 1 is 4, 2 plus 2 isn't 3 plus 1 because 2 is 3 and 2 is 1. It's not always the case that whenever you get equal outputs, there must have been equal inputs. But it is always the case that if you give equal inputs, you get equal outputs. So it's not a free hit. It doesn't just cancel the way it does when you get successors bubbling out the front. You have to choose that that's your explanation. And we've lined it up carefully here so that it's equal outputs because they were equal inputs. This is what happens when you change one small sub-expression by an equation you know. So we say under plus, and ask doesn't give us any sub-goals because A times B is already A times B. That would have been one of them. And it's trivial because left-hand side, same as right-hand side. And meanwhile, the equation A times B times X equals A times B times X is true because it's given inductively. So both of the pieces of the under are straightforward. And so that branch is done. And then what happened was we were left with the other sub-goal, middle to the right, where we see we've got an A times plus an A times on the left, and we've got an A times on the outside on the right. And what we're missing is something you were taught at school, which was peculiarly called the distributive law. And the reason it's peculiar that it's called the distributive law is the definite article. I am going to teach you a great many distributive laws and why they're all that effing same. So Fred had the bright idea that we should just go ahead and prove the distributive law. And once that helpful result was in place, up ahead of the main goal, we were able to comment out the second sub-goal from by root, and Ask was happy with that because it could see that this goal here is a substitution instance of this thing which we are now in the business of proving. So Ask is always happy not to trouble you with something that's an instance of what you've already taught it. So when you see a sub-goal that needs a separate proof, you farm out the separate proof further up the box, and you comment out the sub-goal that now follows from it. I mean, you could even delete it, and Ask will be happy. It doesn't yet say proven here because we have to finish the whole thing. But we are at least in an estate where something good might happen. Okay, so I wanna.
Why does it say tested here?
Right. So the problem is that it's now. My silly goal about Connor and Clemens and Panic and Terror is a very general statement about equations involving plus. So now it thinks we're going to prove that all equations involving plus are true, which is why it thinks this goal is done. So I have to delete Connor plus Clemens equals Panic plus Terror and press send again to get back into the room. Yeah, too much magic.
This group is much shorter.
Too much magic will kill you. Yes. Right. So now we're back in the room. We can see, now let me put the bracketing. Remember we said plus groups to the left. So here we have this. Okay. So I'm going to invite Clemens to take over at the controls. And I'm also going to invite yous to give us a suggestion for what might happen next.
Oops. So we're here somewhere.
We should possibly even say what assumption we're entitled to inductively. Now, let's also recap. We play why is it stuck on this goal. So you can see plus gets stuck when its first input is stuck. So we're interested in A times B. And then A times B is stuck because B is stuck. Likewise, on the right-hand side is stuck because B plus C is stuck. And B plus C is stuck because B is stuck. So that's 2 votes for B, right? Again, not magic. You do this analysis, and then you say, inductively B from B test, and then you switch your brain back on. Right. So brain on, Clemens.
Oh, no.
Right. We know.
Do we know this?
We do know this.
Excellent.
Because C is smaller than B. So X is smaller than B.
Yes.
So we have that already. And you can see,
so
isn't there a lovely A times X knocking around on the left-hand side of it? Can you see anything useful, right? You're always looking for the bits and pieces of the induction hypothesis.
Yeah. Only the bracket is in our way, right?
Yes, the bracketing is in the way, but also on the right-hand side, you can see that the entire right-hand side of the induction hypothesis is just right there.
Ah, yes, here we have it.
So we know a step we can take from the right-hand side that might get us closer to the left.
Indeed. Somebody joined.
Yeah.
Just in time.
Yes.
So how do we get there is the question.
Mm-hmm.
Does anybody have an idea?
What's our move?
I'm just trying to save time. I mean to gain some time to figure out what the next move is.
Well, we want to replace the highlighted expression by the corresponding left-hand side of the induction hypothesis.
Yes, so somehow we want to move those brackets to another point.
Yeah, so that happened too. You can see, I mean, if you just reformulate the right-hand side of the equation by using the induction hypothesis, then you'll see something useful.
Sorry, the right-hand side. What
Yeah, you see the right-hand side, a times x plus c,
yes,
includes the right-hand side of the induction
but
hypothesis.
how do I now use this?
Well, this is a job for by root.
Okay, let's
So,
see. Yes, of course. I mean, I knew by root, but
so yeah, you need to get rid of the question mark, of course.
it's
What always happens. And to be slightly more indented than the P of prove.
by root.
Yes, and then in parentheses,
A. Wait, what do we want?
A plus,
Us,
and then just copy and paste.
Times x plus c or something. Is this correct?
Yeah, you need to group that because plus groups to the left. You need to group that to the right explicitly.
What do I need to do? I need to do this basically.
Yes. So all we're doing is, so hit send.
Oops.
If we've got the brackets balanced, count back first.
1, 2,
3, 2, 1, not one more close. One more
really?
close.
1, 2, 3, 1, 2, 3.
Oh no, you're right. You're right. I can't count.
Excellent.
Hit send. Right. Pregnant pause. While our goal flies all the way over to Livingston Tower, churns for a while, and then comes back.
And what happened?
We got good stuff.
Let's move it back here, except. Is it now there?
Yeah. It would have happened.
Sorry. I'm scrolling normally on my laptop in the other direction, which.
Right. You need to hit accept. Didn't think it registered that. Yes. So Clemens is used to his laptop, and he's also sufficiently not addled by caffeine and alcohol that he can get away with tap click. Whereas if I switch tap click on, my delirium tremens is so bad that all sorts of things happen by accident.
Anyway, we made progress.
Yeah. So we've got two goals which are left to middle and middle to right. And you can see that
the second one is easy, right?
You can see that middle to hang on, something's funny.
Something funny has happened,
right? So this is we transcription error. Huh? So here you've said a times x merely plus c when you meant to say a times x plus
a times c. Yeah, you see.
So yes, that's
because
why
something really funny happened here.
Yeah, so just delete the sub goals and hit send again.
Do you also have to delete the where, or is it fine?
It'll be fine with that. So yes, that was a narrow escape.
Are we there? Wait a second. Accept.
Yes, we are. And you can
what happened now?
You tapped rather than pressing. You'll get used to my.
I think yes.
Yes, or we'll have to get you.
I need to kind of sit down for 1 hour with this laptop, I think.
Right. So now you see left to middle didn't even appear because it was just about reassociating a plus. Right. The left to the middle is just rebracketing pluses. And we already taught ask that plus is associative. So it doesn't show that up. The remaining goal has an A plus on the left, an A on the left of a plus, both sides, and the induction hypothesis essentially to the right of the plus. Indeed. So once again, we finish the thing with under plus.
Like that.
Yep. So
is there space or not?
That's fine. And it'll show up in a minute.
That's right.
Right. And look,
proven.
All of the provens happened. Yes. So here, we are trying to prove this equation. And you can see that on both sides of the equation, we have a plus. And to the left of the pluses, we've got A. And to the right of the plus, we've got this thing on the left and this thing on the right. So under plus is making the explanation that the outputs of these two pluses are equal because the inputs are equal. So we then, the sub-goals we get and don't see are that A equals A, which is just immediate, and that A times X plus A times C is equal to A times X plus C. And that's given inductively. So by splitting up under plus, we've actually knocked the whole thing off. And then let's hit accept. Let's hit accept and notice that not only is distributivity of multiplication over plus proven, but now associativity of multiplication is proven. There was a question, I believe.
Given E equals Z, 3 halves is A times Z plus A times C. And I don't know where it's coming from, I don't know what it means.
So the trouble is that I can't see what's in front of you. Send me a message on Teams. Yeah, so it's really difficult to diagnose difficulties without being able to see what's in front of you. Well, I mean, don't feel you have to figure it out on your own. Drop me a line on Teams, and I'll try and dig you out when the lecture's done. We have to move along to the topic of the homework, which is about formulae, which we're going to, I haven't been to the veg shop, so and also, limes, nectarines, plums, and tangerines are quite juicy, and I'd end up making the bench all sticky if I actually built these things. But this is a kind of new kind. Remember, we made models of numbers with spuds and lemons. Well, we're going to make in our minds models of more complicated things with more bits and pieces, but it's the same kind of stuff. Before we start, can you tell me just using mathematics you learned at school, I've written a formula and I'm asking you what its value is when the variable takes a particular number. What's the answer? 42. We're always trying to angle for the answer being 42. And if you don't know why we want 42, you'll probably eventually figure it out. But okay, so that's the game we're going to play, right? So the point is that the formula just sits there being a piece of text, or rather, it's a structured thing. It's a recipe for a calculation that you're not ready to do yet because you don't know what the variable stands for. Okay? So we're going to say, so the formula on its own, without an interpretation, is just data. All right? So this is how we represent this sort of thing using ask. Just as before, when we say data, and then the next word is the name of a type that we are inventing. So we're saying, I am inventing a new type of thing called a formula. And here's how you can make a formula. The constructor X makes a formula. That stands for the variable. The constructor N, if you give it a number, makes a formula that has a constant value. So you can turn any number into a formula by packing it up with N. And then...
So that might be a bit strange, but...
Yeah, so yes, you might think, isn't 2...
Is it 2 already a
formula? Already a formula. No, it isn't, right? We want to distinguish the number 2 from the formula, which is made by saying, I want it always to be the constant value 2. So you don't have numbers packed up by formula, like formulae with no notation. That move of saying numbers embedded into formulae, it's informally we just write numbers down, but formally we have to notice that that's what's going on, that we are saying we're making a formula out of a number. And then there are 2 ways to make formulae out of 2 subformulae, namely colon plus colon and colon star colon, which are, funnily enough, going to turn out to be interpreted as adding and multiplying, hence the suggestive names. What's this colon business? For infix operators, so you know this distinction between words which begin with lowercase and words which begin with uppercase. So the uppercase things, the capital letter things, are like proper nouns. They just stand for themselves and their job is to be different from each other. Whereas lowercase identifiers are variables. They stand for something other than themselves, either by definition or because they are pattern variables on the left-hand sides of the equation. Well, the same distinction between proper nouns and common nouns, but for operators, is given by whether there's a colon at the start of it or not. So if you see an operator that begins with a colon, it's a constructor, and it's just a lump of data that happens to take 2 inputs. So this colon plus colon and colon star colon, it's not doing a calculation the way plus and times do with numbers. It's just saying, oh, this is a formula that says something plus something, or something times something. So it just sits there being like the text of our x plus 2 times x plus 3. Okay, so I'm going to write down that formula. So that's x plus the number successor of 0 times x plus, copy, paste, and then we wrap another spud around the number. And then to make it not look awful, I take a new line and indent a little. And now I hit send. And we wait to see what happens. Come on.
Today it's very slow.
Yeah. Oop.
Oops.
And then what have I? Oh, I've been very silly. I've written just a plus sign here, which is the operator that adds two numbers. I'm trying to say the formula that uses the addition operator for formula. I forgot my colons, and I didn't even do that deliberately. So, plus adds numbers. Colon plus colon makes a big formula from two small formulae. Right, now we're happy. So I'll say accept. Okay. So then here's our next task is to get us closer to that 42. We need to explain how you figure out the numerical value of a formula when you know the numerical value of the variable. So that's the job of this evaluate function. We need to evaluate the formula given what number the variable stands for and to give the value of the whole thing. So how do you think we should proceed?
I guess inductively.
Inductively, but on what?
That's not so easy, but I would say on P in this case.
Yes. We figure, I mean,
because there are two things which are inductive,
yes.
right?
Yes.
So how do I know that I shouldn't go to the end?
Yeah, I mean, so but think about how you actually do this computation. How did you figure out that x plus 2 times x plus 3 was 42 when x is 4, right? You didn't start by thinking, oh, what would it be if x was 3? Right? You thought, oh, how does this calculation come apart into pieces? So yeah, we're going to go inductively on P.
Wait,
the formula.
P, right?
Yeah.
Yes.
And then you hit send.
Oops.
Is it? Yes, it's doing something.
It's doing
just
something.
Slow.
It's
just slow.
But it jumps then there. And then
yeah. Okay. And then you. So far so good. Hit accept. Okay. And then by the same token, we are actually going to want to look at the formula. So that's a job for from. Yes. So here, the plum looks like colon plus colon, and the tangerine looks like colon times colon. So these different fruit turn into different constructors of the data type, which have to be textually different. So when Clemens sends from P, so remember, in a program or in a proof, from is short for where does this come from? And what use is it to me? So we've got, so we hit accept, and you can see we've got 4 cases for the 4 different possibilities. So, and it, of course, chooses terrible names. I'll fix the names.
Okay. So
let's have Q's, and it's my fault that the names are bad, so I'll fix them. Right. That's nicer. Right. Okay. So,
thanks.
let's work through these things. Oh yeah, I'll change this name as well. I'll change this to the suggestive C for constant. Or it should be K for constant, of course. Right. So, not a trick question. If n is supposed to be the value of the variable, and the formula we're looking at is the variable, what should be the value of the formula? N. Yes. So let's do at least the first 2 before we hit send, just because it's so slow.
Okay.
Right. Right. Now the formula says I am the numerical constant C.
And X is N.
and X, the variable, if it were to show up, would be worth N, but it hasn't shown up. The formula is just the numerical constant C. So what's its value? C. Okay.
Should we hit
Yeah,
send?
hit send.
Sit help.
And
Something will happen eventually.
yeah.
My brain can't cope with this way of scrolling. Wait a second.
Yeah, it's other people's computers are hell. It's not quite, yes. Okay. But yeah, we'll try to do that, although we don't have terribly much time. Right. So now our formula says Q plus R, and we know still that N is the value of the variable. How would you do this calculation? If you see a formula that something plus something and you evaluate it, what do you do? I mean, there's really only one thing you can do that's vaguely sensible. Yeah, so yeah, right. But the point is, the formula says something plus something. So what you're going to end up doing is substituting the number into both pieces, evaluating them separately, and then adding the answers. You know, isn't that what you did when you were figuring out that x plus 2 times x plus 3, what that is, when x was 4, you thought, oh, well, x plus 2, that'll be 6, and x plus 3, that'll be 7. And then you multiplied them. So you figured out the values of the subformulae and then combined them in some way. Well, same deal here. And we are allowed to evaluate Q, and we are allowed to evaluate R because they're smaller than P. And we said inductively P, so we are entitled to evaluate simpler formulae than P. And we figured out that P is Q plus R, or P is Q times R. And let's do multiplication as well, because otherwise.
Otherwise, indeed. Okay, so what I can do for multiplication, if I'm
You
smart,
can copy and paste.
I copy and paste it. And now,
it's squiggly.
Wait.
Command
What's
C.
this? Command C.
And then Command B. It's a Mac.
Now the times is defined as a plus.
Yes.
But now it's defined as a times.
Yep.
Send.
Right. Tension.
It's defined.
It is defined. Okay. And now let's see if we are lucky. We still have our definition of 4 from before. So now we should be able to say test, evaluate, example 4. And then we wait with bated breath.
And if it's not 42, what do we do?
We cry. We hit accept, and that's an awful lot of S's. But I'm going to do this. Just split it up. Notice I'm not deleting anything. I'm just putting spaces in. 7 S's to a row. And 6 rows of S's. That certainly is 42. Thank goodness for that. We got 5 minutes to go. I know I wanted to actually have a go through the last week's tutorial homework, but in 5 minutes I don't have time. So that's the shut up alarm. Which because I like to be a decent kicker outer. When I started as a lecturer, I was a rubbish kicker outer. and I was often bullied out of the room I was in by the next lecturer, who was an economist who wore a patterned waistcoat.
I know the guy.
And a particularly smug expression. He would very sarcastically tell me that I wasn't doing my job right. And I just thought, I'd never want to be that person, but also I never want to be told this again. So I got better at kicking out. Anyway, I want to have a quick look at, if I can find it, at this week's tutorial homework, which I hope you will not be too phased by. Come on. Because this week's homework involves formulae. And I hope it will appear at some point. So I give you all sorts of stuff, I give you formula, and I give you the function that we've just written, but I want you to define a thing called substitution. And I've got this little symbol for substitution. So P substitute Q says, I've got two formulae, P and Q, and I want the formula that you get when you replace every occurrence of the variable in P with a copy of Q. So do you remember when we were adding? We said we want to replace the left lemon with the right number. Well, this is just the same thing again, except that instead of there just being one lemon at the end of the number, there are some number of occurrences of the variable in the formula, and you need to replace all of them with Q, and the rest of the formula stays the same. So if you can add, you can substitute. It's the same process. So please don't be freaked out by it. And guess what? It's got a neutral element, and it's associative. You might see that there's a bit of a pattern. And then there's a connection between the substitution and the evaluation. Because funnily enough, it'll turn out that when you evaluate the neutral element of formula, you get the function that does nothing. So there's a formula that makes substitution do nothing, and when you evaluate it, it gives you the function that does nothing. Nothing will come of nothing. And likewise, when you evaluate the result of substituting two formulae as pieces of text, you get the function that actually pipelines the computations done by the two formulae. So putting formulae together in a row gives you computations that come together one after the other. It's almost like there's some structure. It's like we're doing this deliberately, with a pattern that we're paying attention to. And that's what CS103 is really about. CS103 is about doing things deliberately. I'm trying to teach you to do things deliberately in order to make the world less full of shit. Here endeth the lesson. No.